Okay, hello everyone. Today I would like to show you my pre-thesis topic. My topic is about the deep learning, and for specifics, it's about recurrent neural network (RNN). So in this presentation, I will bring to you three main parts. The first is introducing to the RNN in the sequence mining. Next, I will introducing to the long short-term memory. Then finally, I will show you uh, introduction to the incremental learning. So we are going to the content. In my content, we have five parts. First, the introduction. Then I will show my related work, and then also my proposal. And the next one is result, and finally is the demonstration. So we are go to the introduction. There are three main tasks for my topic. First is about study in the recurrent neural network. And in this one, I will research the basic knowledge on the recurrent neural network for the sequence mining data. And then I will implement one LSTM uh, demo. For the second one, I will show you the basic knowledge about incremental learning, and later on I will do the incremental RNN. So the related work, I use to review the basic knowledge, to prepare for the deep learning, the first about the linear algebra, calculus, probability, and also machine learning algorithm and optimization technique. Then I also review on the neural network, the artificial neural network, for the first month. Then for the second month, I study recurrent neural network and LSTM. Then I'm doing on the incremental learning. So I also implement the one example. Uh, this is the network prediction and sentence completion example using the TensorFlow and NumPy framework on Python. About proposal, I decided to continue on research the incremental recurrent neural network methodology in the sequence mining. Then I will implement the incremental sentence compression using LSTM. And in the future, I would like to combine the RNN with also the CNN to implement a new solution to describe the image. So now we are going to about my results on the RNN. So first, uh, before moving to the RNN, I would like to talk a little bit about the ANN, artificial neural network. So as you know, on neural network, basically neural network consists of one input layer, uh, one or more hidden layers, and one output layer. And you can see on the figure on the right side, this is a basic figure structure of the ANN. We can easily find that uh, its input from the input layer and output are independent. Thus, they have no relation between each other. So, our problem is showing the sequence information processing problem by the neural network. So, we can easily see that this model cannot be solved by using the basic ANN. That's why the RNN appear to solve that problem. So I'm going to talking about recurrent neural network. So uh, before um, I moved on to the recurrent neural network, one thing I want to mention is important of what embedding for the recurrent neural network uh, in the concept of natural language processing. Uh, so the RNN are designed to solve the sequence information processing problem such as predicting the network in a sentence, uh, The right sequence of work that came before is become paramount importance. And actually, the RNN is applied most in natural language processing. Uh, to easy understand for this RNN, I will give you one simple example here. Uh, I give a input collection that have four character uh, like this. So our mission is using the neural network to complete a word with this red character to make a complete and meaningful word by a neural network. So this is a model that how can this work from the RNN. So the rule you can see first the character are encoded under one hot encoding. This technique I can discuss later, but basically it will return the value 1 if the letter appear. So the rule is that we find out the next character with the highest probability by softmax. Softmax. Uh, in this case, the input chart is so the net prediction chart E. The key point is that E become a net input of a network. This is the main difference compared with the uh, basic neural network. So here the architecture of the RNN. The key point of difference is that the RNN has the unfold. In the figure, the RNN architecture has been unrolled in time to depict the complete sentence. If we wish to, for example, if we wish to resist 7 word sequence in of a sentence, then the unfolded RNN architecture would represent a 7-layer feed-forward neural network, with the only difference being that the weight of each layer are common shared weight. The significantly reduce the number of parameters to learn in a RNN network. So to get just to get us familiar with the notation here, I talk about first the first the ST represent the input, then uh, the HT represent the computed memory, or we can use always connect the hidden state. Then the OT is the output, uh, respectively respectively as time step T, and the W represent the weight matrix. So as you know, in the also the same in the neural network. So let me talk about the formula here. So uh, for the ST, the input ST is a vector represent the input word as step T. For example, it can be one hot encoded vector as I talked before. Uh, with the component set to 1 for the corresponding word index in vocabulary. It can also be the word vector embedded from some retrained repository. So in general, with some ST in one dimension vector. Also, if we are looking for reduced B classes, then the output YT also in 1D one dimensional matrix. So the memory or the so next the memory or the hidden state vector uh, ht can have any length as per user choice. uh, the weight matrix connecting the input to the memory state, and the weight matrix connecting the memory state to the output. So I show you the memory equation as step t is computed like the first formula. Whenever f is a non-linear activation function, we have some function e usually applied. This is a sigmoid function and time function. Both of them are also the logistic belong to logistic function. So talking about the related output, the connection from memory state to the output are just like the connection from a fully connected layer to the output layer. When a multi-class classification problem is involved, such as repeating the network, then the output layer would be a huge submap of the number of words in the vocabulary. In such cases, the related output vector O is uh, belong to the V one, the also one dimension vector. So it can be expressed as submap functions. So I write here whenever the BO here is a bias vector from the output unit. So from that one, similarly, you can add a bias to the memory step. So the third one is a loss as each time step can be expressed as the third formula, and to get the on overall loss over on time step t, t needs to be sum of the average out. So generally, the average of all systems are more convenient to a stochastic gradient descent. So we're talking about gradient descent. So as to get a fair comparison when the secant length vary. So this is the formula for the overall loss. So next one we will move to the long short-term memory, LSTM, and basically the LSTM special version that can learn distance dependency between word and sentence, and it's a wide bit different traditional RNN. So to be more specific, we are going to find out what is the difference in the formula. So in the LSTM, the basic building block of the function are here. The first I want to say is the new element in the LSTM in the introduction of the cell state. Here is CCT, which is regulated by three gates. The gates are composed of the sigmoid function, so that they output values between 0 and 1. So as second step t of the input st and the previous step hidden state s decide what information to forget from cell state ct-1 through the forget gate layer. So we have the different definition about forget gate layer. Then the forget gate look at uh, the input st and the hidden state at time step t-1 and assign number between 0 and 1 for each element in the set state vector c t-1. An output of 0 means totally forget state, while an output of 1 meaning keep the state completely. So that's why we have the function of forget state and follow the first formula. Next one, the input gate decide which cell unit should be updated with the new information. For this, like a forget state output, a value between 0 and 1 is compiled for each cell state component through a following logic. Like IT also the same with the first one. So we have another definition about the candidate cell state. So a candidate set of new value is created for the cell state using the input st and the hidden layer as t-1 as input. So that's why we have the candidate cell state compiled by the time function. The new cell state is described as follows. Uh, and the output state is nothing different from the RNN. That's as I said before. Uh, the update hidden state ST can be built from cell size C by passing each of its element through a time function. Then we do in an element Y product with the output K value. That's why we have the update hidden state formula like the last formula on the screen. Uh, Please be careful that the denote star, the symbol star in this formula, uh, which denote the element y multiplication, not the usual multiplication. This is done. This is done so that based on the gate output, we can assign weight to each element of the vector is operating on. Also note the whatever gate output values are obtained, they are multiplied as the gate outputs are not converted to discrete value of 0 and 1, continuous value between 0 and 1 through sigmoid rovine smooth gradient for backpropagation. In LSTM, the forget gate play a crucial role in LSTM. When the forget gate unit output 0, then the recurrent gradient becomes 0 and the corresponding cell state units are discarded. By this way, the LSTM throw away the information that it is not going to be useful in the future. Also, when the forget gate output unit output is 1, the error flow through the cell units unattended, and the model can learn a long distance correlation between temporary distant world. Uh, Too easy to understand, we will discuss more in the demonstration. So next, I want to talk about incremental learning. That I'm also start to research on this. Basically, the incremental learning is how you can let the input data continuously use to extend the existing model knowledge. Um, for the purpose, the incremental learning can adapt the new data without forgetting its existing knowledge, and it does not retrain the model. And basically, we can find out easily that the model can be become bigger by the time, and it's also applied in the most in the data stream or big data. So next one, I will show you one demonstration of the LSTM to reduce the network and session complete. So they say it's just only a simple paragraph I guess from Alice Wonderland book like here. So I will change move to my IDE to show you my demonstration. So here the demonstration code. First, I would like to use some familiar library like NumPy and TensorFlow. Also the library of Python. I assign to the running rate is 0.001. I use 50,000 training iteration. But I also deploy after 500 steps. And n input is 3. The meaning is using 3 words to read the next word. If we input 3 words, 3 input equal 1 output. It's easily like this. The unit in the RNN cell are size 512. The function to read data, this is the data under the ND array of Python. Building dataset return the dictionary of collection of the data After reading the data, if we collect the word and return dictionary and also reverse dictionary. About the input one hot, it's easily here. It's just return the value of the word equal one if it exists in the this one, and for the left it returns 0. So the input here back the input, read the training data, then building the data set, return the vocabulary size. I remember that my test contained 174 word. So placeholder for the mini byte input, the input, the y vocab size, aside for the weight and also the bias, it's necessary. So about the RNN here, unstack then run the RNN cell of RNN. I use the RNN function of TensorFlow. The output state return the static RNN and return a math multiplication function with the weight and also the bias. I also write the loss and optimizer function to show how much loss after each iteration, and so write down on in the output. So let's go to the main functions. Here the step, the offset, the accuracy total, the loss total, and I run the training in this part. I run this one, and first is in boot one hot dictionary for the range of the offset, and offset but the input. After training 50,000 iterations, it returned the result. I show you it's returned after 500 iterations. It show the result one time, and after finish the training, I try to read it one sentence. The next 28 words of one sentence, and I also run this already, and it return result like this. So let's go back to the first. You can see in the first iteration is some first iteration is average accuracy is still low, but only for more than 2000, and it return a higher rate that can match our requirement, and continually after 50,000 iteration it return a very correctly accuracy. So here the complete sentence follow, and it's also made uh, with the text I highlight here. That's in my demonstrations. So you can I want to summarize this. My the RNN accuracy in this demonstration raising weekly, and the revision didn't start well with the first two words, but it did an excellent job for the rest of the sentence. I think this brings me to the end of my presentation. Thank you for listening.